Hi, my name is Hasan Koçer. I'm from Selçuk University from Turkey. The title of my presentation is Design and Implementation of a High Stability Laser Diode Driver and Precision TEC Controller for Tunable Diode Laser Absorption Spectroscopy. First of all, I would like to mention about TDLAS. It's a tunable diode laser absorption spectroscopy. It is widely used in gas detection applications. It has a high selectivity, fast response time, and low detection limits. The success of this method depends on maintaining the wavelength stability of the laser diode. There are two main factors that affect wavelength stability are noise in the current drive and fluctuations in the laser temperature. In this study, we present a low noise, high stability laser diode driver and thermoelectric cooler TEC control unit providing 0.001 centigrade degree temperature precision. And it's designed and tested on TDLS LAS based methane detection system. The laser diode driver was implemented using feedback controlled op-amp and operational amplifier and MOSFET-based constant current source architecture. And plus and minus 2 ppm current stability was achieved using a precision metal foil current sense resistor. Design supports both constant operating point and wavelength scanning functionality through DC bias and 10 kHz sinusoidal modulation input. The proposed TDLA system was shown in this graphic. It's designed to enable high precision methane detection with long-term wavelength stability. The designed system was set up consists of two major subsystems. One of them is a low noise laser diode current variable based on a feedback controller, op-amp and MOSFET constant current source. And the second one is a high resolution thermoelectric cooler control unit implementing digital PID regulations. Both units were integrated into a single PCB to minimize the electromagnetic interference and optimize thermal coupling with the laser package. The output was connected to a methane gas absorption cell with an optical path length of 3 centimeters, and transmitted intensity was monitored using an in-gas photodiode connected to a transimpedance amplifier. And also a RC filter was used in this system. It is a 60 kilohertz low pass RC filter. It's used for isolate high frequency switching noise from the power supply. And we used TAC module mounted inside a laser diode for achieving the temperature stabilization. The temperature was measured by a 10 kilo ohm NTC thermistor placed in the laser diode, and control was implemented using a microcontroller STM32 STM32H series microcontroller, and we used a digital PID algorithm for control the system. The output of the controller was applied to Hash bridge MOSFET driver operating 20 kHz PWM frequency, and spectral scans were performed by applying 10 kHz sinusoidal current modulation superimposed on the DC bias. The TEC maintained constant temperature. The acquired data were processed in a microcontroller unit to extract the absorption spectra. We also use to control the temperature thermoelectric cooling technology based on Peltier effect. Peltier element, as you know, electric cooler. It's the principle is when we use an electrical power, the PN thermocouple layers shows a heat flow. So these thermocouples are electrically connected in series to ensure a uniform current flow. The materials are encapsulated between two ceramic plates, and electrically they act as insulators, preventing short circuits. The resistance and temperature graphic is shown below, as you can see. For system validation, we used output power of 1653 nanometer laser diode, and it's divided to both system and optical power was directed through a reference gas cell filled with methane, as you know, as you see from this figure. And the overall electro-optical configuration is illustrated besides. There is a data acquisition card port connected to the PC and a laser controller. Here we used also a photodiode and with a lens. There is a coupler for coupling the laser diode. Then we use a filter to get the surface light lines. The absorption profile was continuously monitored by the gallium arsenic detector inside the reference gas cell, enabling precise identification of the maximum absorption point. At this point, the corresponding drive current and TEC set points were recorded as calibration parameters. This calibration cycle is automatically executed at each system power-up, ensuring wavelength stability and repeatability of the measurement system. Now we will look the findings of this research. The designed laser diode driver and TEC controller were experimentally validated under operating conditions relevant to methane detection using the TDLAS technique, and we use oscilloscope to measure the achieved low noise current output. This figure presents the temporal trace of the laser diode temperature, demonstrating negligible deviation and the absence of oscillatory instabilities. When we use this graphic, 25 centigrade degrees, the stability can be seen from this figure, from this graphic. Then we use a PID algorithm to control the to control the system to maintain the diode case temperature stability. Local real-time temperature data validated the proper tuning of the PID coefficients. 20 kHz PWM operation ensured the minimal thermal ripple. In contrast, when inappropriate PID parameters were selected, unstable oscillatory behavior in the diode temperature was observed. As you can see, the temperature, diode temperature was rippled during the time. For optical validation, the calibrated 1653 nanometer laser output was partially directed into a metal reference gas cell. The oscilloscope traces of the photodetector signal, and we get the ripples here, as you can see from the figure. The repeated calibration cycles following multiple power-up sequences confirmed consistent wavelength, looking to the absorption line with deviations below minus and plus for 0.4 pm. The figure shows the output of the reference gas cell when the laser diode was driven with the correct current and maintained at a stable temperature of 25 centigrade degrees. And this figure illustrates the reference gas cell output when incorrect current and temperature values were applied. In this case, no absorption-induced depressions are visible in the modulation signal, as you can see, indicating the inability of the system to perform methane detection under such conditions. These results demonstrate that the proposed driver and TEC controller provide not only excellent electronic stability, but also high optical precision. The findings confirm the system's suitability for long-term, low concentration gas detection applications where both current noise and temperature drift represents critical limiting factors. As we can conclude this study, we can say that this work demonstrates the design and validation of low noise laser diode driver and high precision TEC controller for tunable diode laser absorption spectroscopy based methane detection. These results ensured reliable wavelength locking with deviations below minus and plus 0.4 pm, enabling the accurate detection of methane absorption features at low concentrations. The successful and repeatability detection of methane absorption line at 1% concentration level with a wavelength stability below minus and plus 0.4 pm throughout extended operations, and the achieved performance levels specifically 0.002 centigrade degrees thermal stability and also sub 1 microampere noise are essential for maintaining the sub ppm detections limits characteristics of TDLAS. The study confirmed that both current noise and temperature drift are critical factors in TDLAS systems. Incorrect driver current or poorly tuned PID coefficients led to loss of absorption signals, highlighting the importance of precise electronic design and thermal management. Yes, my presentation is now finished. We make a study on tunable laser diode laser absorption spectroscopy with a TEC controller. Thank you for your listening. That's all.